Thus far, we've looked at the properties of individual neurons or units, the similarities between their properties and the properties of neurons. We've looked at how those neural systems can be organized out of those individual units to create, in effect, computational devices in the same way that neurons can be assembled together to create a computational device. Now we want to look at representations. How is it that such systems represent things? And we want to talk about specifically, in this case, representations for the input layers and the output layers, inputs and outputs. And we'll do that by talking about vector coding sort of specifically. We'll distinguish between distributed and local representations of objects, properties, and relationships within that framework of vector coding, and then talk about the role of compositionality and how the compositionality of vector coding differs from that of something like a language. So the nervous system and our neural network systems are going to represent by altering firing rates or activation for different neurons. Information can be encoded by individual neurons or by collections of them. And in each case, part of their function is to carry and process that information. So when groups of neurons act together to represent properties, they're often said to create a representational space, where each neuron that participates in that representation is said to represent a dimension or to create a dimension in that space. A given object or property can be represented in a representational space by the activation pattern across that set of neurons then. And that activation pattern will pick out a unique position in that space. Each position is then thought of as a vector, a line from the origin of the space to that position. And this sort of representation is often therefore called vector coding. Now, vector coding has three important elements. You have to have multiple dimensions, multiple units. Each dimension has to have more than one value, and those values have to take on a metric greater than or less than. So here's an example from Paul Churchland. This would be a representation of taste within a taste space. So sensors on our tongues that are sensitive to sweet, to salty, and to sour in combination can encode a whole range of different tastes for different kinds of substances. So here we have, for example, urea. It's a little bit salty, a little bit sour, a little bit sweet. Fructose, very high on the sweet scale, not too high on the salty scale. Table salt, very high on the salty scale, not too high on the sweet scale, and so on. And so the activation patterns, how they activate these individual sensory cells in a pattern, that creates a representation of the taste of that specific substance. Similarly, we can use color opponency to represent colors in a color opponency space. And here we have one dimension, which is white, black. So black is all the way down here, white is all the way up here. White, black, gray is in the middle. We have a red-green opponency, such that red is over here on this side, green is over here on this side, and then their intermediate yellow would be over here on this side. And similarly, we have a yellow-blue dimension. Yellow would be over here, blue would be over here. And we can represent all sorts of different colors, as this diagram illustrates, in virtue of where it is on the black, white, red, green, and yellow, blue opponency scale that this color happens to lie. So white is at the top of the white. It's neutral between green and red and blue and yellow. Whereas yellow is in between red and green, but it is all the way over here on the yellow side. And a light green would be halfway up between the black and white periphery. And so in this case, we have representation of colors by representation of their opponency. And this is in fact the way it looks like primate vision works. Here we have parvocellular cells in the retina, and we have these color opponency cells. We have these on and off center cells, and they are tuned, in this case, to stimuli of particular wavelengths. So here we've got a red cone, and it is sending activation down to these two different ganglion cells. And they have different reactions to that red stimulation based on the color opponency that they have. So here our red on-center cell, it gets its activation from red, that excites it in the center here, but it has inhibitory blue and green on its periphery because of this horizontal cell here that affects its firing when these are active. And similarly here with our opponent cell that is off center for red, it's got the red cone coming in and that inhibits it, and then it's got this horizontal cell that excites it when there are green and blue out here in our periphery. So we can see how the different activation patterns of these different three cells and the relationships that can be created computationally with just the use of a couple of other different intermediate cells, how that can create this color opponency, this on-center, off-center, red-green opponency. Neural network systems are going to represent objects and properties by activating units in a particular layer in some pattern. And just as firing rates of groups of neurons can pick out positions in representational space, activation patterns across units in an input or output layer can pick out positions in a representational space for that input or output, where each dimension corresponds to a unit or units in the layer. So in modeling, then, neural network theorists can choose to represent objects and properties in two ways, and we'll look at this in the next module of this lecture. They can represent locally or they can represent distributively.